In this slide, we'll examine convolution for periodic sequences. Let's assume that we have x of n and h of n, and we remember that y of n is the convolution between x of n and h of n. It's given by this expression here, and you realize that we need to sum for infinite index k. So if x of k is periodic, then this sum would not converge. So what happens, or even if h of n is infinite, this sum will also not converge. So the summation fails when both the signals x of n and h of n is periodic. So what happened, and what should we do if x of n and h of n is periodic? Because if I give you a sinusoid, then x of n is periodic. So we can't solve this. So what should we do? Well, in the case when we have periodic input and or h of n, we can define something called a periodic convolution. And the difference between a periodic convolution, first is the notation. The convolution was that little star here, now becomes the cross with a circle. Additionally, we want to very clearly indicate that x of n and h of n are periodic. We add a tilde here to indicate that it is repeating. And most importantly, we do not do for infinite k index anymore. We only actually do it for one period. Here, k equals to 0 to n minus 1. We assume that both the sequence is periodic n. And then now we can write this equation. Okay, so what should we do? Well, basically you take one period of xk, and then we are shifting h of n minus k. So it is the shifting that is the difference between these two. Later on you will see. That causes, that is the key difference between periodic convolution versus linear convolution. Right. So let's examine. Let's have x of n that is period n equals to 5. So 0, 1, 2, 3, 4, repeat 0, 1, 2, 3, 4. h of n is also period n equals to 5. Its value is 3, 3, minus 3, minus 2, minus 1. 3, 3, minus 3, minus 2, minus 1. So both are periodic with period n equals to 5. Let's take the convolution between the two, and we just take this expression. Then this is the definition, and now we substitute. So this is easy. X tilde k equals to 0 to here is 4, because it's 5 minus 1 is nothing but taking these blue samples. But what about h n minus k? Remember, n minus k means that we are delaying h of n by k samples. So we are shifting the whole thing right. Let's observe. H tilde of n minus 0 basically is exactly the same as h of n. There's no difference between here and here. The 2 blue on top with 3 blues below. And that little arrows showing us where is n equals to 0. What about n minus 1? We are shifting by one sample to the right. n minus 2, we are shifting 2 samples to the right. n minus 5, actually, we now have arrived exactly one period. And in fact, this 5 blue is the same as this 5 green now. Alright, if you do this carefully and this sum, you realize that what we are doing is this is x of 0 multiplying by this sequence plus x of 1 multiplying by this sequence plus x of 2 multiplying by this sequence until x of 4 multiplying by the sequence which we didn't draw. This expression over here, sum of x of k, so I should put tilde here, and each of these element, what is x of 0? Which is 0. So And what about x of 1, which is 1? And what about x of 2 is 2? We are actually scaling a delayed version of h of n. So this is the first coefficient times this entire sequence. This guy is times the entire sequence delayed by one sample. This guy is x of 2 multiplied by the delayed version of h of n by 2 sample, and so on. So this expression is actually just doing this. Now if you do all this very carefully, you'll get the result, which is minus 2, minus 17, minus 2, 8, and minus 13. We plot this in blue. And you will realize that if you extend n, it will repeat. So the 5 sample periodic for the output is also 5 sample periodic. So go through this and you get this answer. There's a faster way. X is the input, which is 0, 1, 2, 3, 4. H is 3, 3, minus 3, minus 2, minus 1. 3, 3, minus 3, minus 2, minus 1. Remember, when we take the FFT of X and FFT of H, we are assuming that we are taking DFT, and we are actually pretending that this sequence is periodic. But this sequence is periodic. So FFT of H and FFT of X is actually representing the DTFS, or the Fourier representation of X and H. By multiplying, here dot star is multiplying element wise, we are actually getting Y. And Y is the DTFS of small y, which is periodic. And to get small y, we are doing inverse Fourier transform, and we get this sequence. Exactly like how we have done if we have done it in the time domain. So you realize that using convolution in the frequency domain is okay if the input x and the input h is periodic. And this is totally fine, and the answer is correct. However, later on you'll realize that most likely x is not periodic or h is not periodic, and the answer cannot be gotten by this way. We'll come to do that later on. Thank you.